Welcome to another deep dive. We're really thrilled to have you with us today because we have a truly mind-bending mission ahead of us. We are peering directly into the future of global connectivity.
Yeah, it's a big one today.
It really is. I mean, if you've ever felt like your current cell service drops out at the absolute worst possible times, or, wondered how a city full of self-driving cars won't just instantly crash the power grid and the internet at the same time, you are in the right place.
Definitely.
We're going to explore the exact nuts and bolts mechanics of how our world will transition from the classical networks we use right now to the absolute science fiction realities of 6G and eventually the 7G quantum communication era.
It is a massive technological leap. Honestly, arguably the most significant infrastructure shift since the invention of the internet itself. And to guide us through this transition, we are looking at an incredible stack of sources today.
Oh yeah, you brought a mountain of reading.
I did. We're analyzing highly technical executive digests, architectural schematics covering quantum 7G architecture, detailed diagrams of 6G AI native ecosystems.
The deep quantum neural network stuff.
Exactly. Extensive research on the evolution of deep quantum neural networks, and some truly cutting-edge papers focused on quantum spectrum management.
Okay, let's unpack this, because I know that sounds like a formidable wall of technical jargon.
It is a lot of math.
Right. We're talking about quantum states, neural networks, 7G ecosystems. If you're listening to this and thinking, I need a degree in theoretical physics just to understand what my next cell phone bill is paying for, don't worry. Our goal today is to take these dense, highly complex mathematical and physical concepts and translate them into clear aha moments.
No textbook reading here.
Exactly.
Okay.
We're going to show you exactly how this invisible architecture works, why it's necessary, and how it is going to fundamentally change how you interact with the physical world.
And understanding that transformation actually begins with acknowledging a rather harsh reality. Classical computing and our current network infrastructures are currently hitting a brick wall.
It's a massive one.
Yeah. They simply cannot sustain the demands of what the near future is promising. We are facing what the architectural schematics we're reviewing call the classical bottleneck. It's an existential crisis for global communications.
I think we need to start right there, because when we talk about 6G and 7G, we aren't just talking about downloading a video faster. We are basically asking our current classical networks to do the impossible, aren't we? What exactly is this bottleneck in physical terms?
Think about the sheer density of the network. Network density is scaling exponentially, not linearly. Consider how many devices are in your home right now compared to 10 years ago.
Oh, it's ridiculous.
Right. You probably have a smartphone, a smartwatch, a smart thermostat, maybe smart light bulbs, a laptop, a tablet. Now multiply that localized density across an entire smart city.
It's millions of connections.
Billions, eventually. We are talking about thousands of autonomous vehicles continuously broadcasting their location and velocity, millions of industrial IoT sensors monitoring infrastructure, and millions of people streaming high-definition, perhaps even holographic content.
And our current networks just can't handle that.
Our classical networks, which rely on rigid linear processing, are descending into chaos under this weight.
And what does that chaos look like on the back end? Because to the user, it just looks like the buffering wheel of death or a dropped call.
On the back end, we are seeing massive latency spikes, severe resource congestion, and devastating packet loss. The routers and base stations simply cannot route the traffic fast enough. And the reason for that is deeply mathematical. Classical algorithms are hitting something called the curse of dimensionality.
The curse of dimensionality. It sounds like the subtitle to a sci-fi fantasy movie.
It does.
But I imagine it's a very real headache for network engineers. Let's break that down.
It's a mathematical nightmare. In classical computing, complexity in these types of dynamic routing problems scales at a rate of O(n) factorial.
O(n) factorial with an exclamation point.
Exactly. That exclamation point signifies factorial growth.
So not just exponential, factorial. For the listener who might be a bit rusty on their calculus, what is the practical difference between exponential growth and factorial growth when we are talking about a network?
It's the difference between a steep hill and a sheer cliff. With exponential growth, like 2 to the power of n, things get big very fast. But factorial growth, n factorial, means n times n minus 1 times n minus 2, and so on.
Right.
Let me put it in perspective. If you have 10 devices trying to find the optimal path to communicate, 10 factorial is about 3.6 million possible configurations.
Okay, 3.6 million. Computers can do that.
They can, but if you add just one more device, 11 devices, it's not just a little harder. 11 factorial is almost 40 million.
Oh, wow.
By the time you reach 20 devices, you are dealing with a number of configurations larger than the number of grains of sand on Earth.
Okay, so it's like trying to navigate a sprawling city where every single time a new car pulls out of a driveway, a completely new, parallel physical dimension of space is instantly created.
That's a great way to look at it.
And your GPS system now has to calculate the fastest route across all of those overlapping dimensions simultaneously, checking every single possible interaction between every single car. Eventually, the GPS processor just melts down.
That meltdown, that freeze, is the classical bottleneck. High-dimensional data in a 7G environment creates computational roadblocks that standard neural networks running on silicon chips processing ones and zeros simply cannot resolve in real time.
Because it would take thousands of years.
Exactly. By the time a classical computer figures out the optimal way to route a packet of data to an autonomous car to tell it to brake, the car has already crashed.
Which is terrifying.
Yeah.
And that brings us to the solution presented in our stack of research. This freeze is exactly why the fusion of quantum mechanics, specifically harnessing parallelism and superposition with artificial intelligence, is not just a neat idea. It is the only viable path forward to engineer this 6G and 7G ecosystem.
Yes. You can't just build a bigger classical computer. You need a fundamentally different type of computing.
You have to change the physics of the computation itself. And the sources we are reviewing outline a next-gen technology stack framework to solve this factorial cliff, and it's systematically built on 3 distinct layers.
I'm glad you brought up the layers because this structure is key.
I want to spend significant time walking through these layers because this is literally the blueprint for the next century of human communication. How is this stack organized?
Layer 1 is the mathematical foundation. This is the theoretical bedrock where we utilize tensor networks to solve the quantum state complexity.
Okay, math foundation.
Right. Layer 2 sits above that as the algorithmic engine. This layer employs hybrid quantum neural networks to actively optimize the 6G and 7G data routing.
The engine itself.
And finally, layer 3 is the physical edge. This is where the math meets reality, bringing intelligence into the physical world with applications like intelligent wireless power transfer for autonomous systems.
Okay, before we get to the physical edge, and we are absolutely going to dive deep into that wireless power transfer because it sounds like literal magic, we have to look at layer 1, the mathematical foundation.
Yeah.
Because I read the schematics, and it turns out even quantum computing isn't a magic bullet. It has its own version of a brick wall, doesn't it?
Yes, it does. What's fascinating here is that even when you make the massive technological leap to quantum processing, you face the quantum scaling problem.
Right.
The sources highlight 2 massive systemic threats to deep quantum circuits, the exponential wall and barren plateaus.
Let's tackle the exponential wall first, because I thought quantum computers with their qubits were supposed to easily handle exponential problems. Why are they hitting a wall?
Well, they handle certain problems incredibly well, but simulating or managing massive entangled quantum states still requires resources. As you add more qubits to a complex system to handle more network devices, the state space, the sheer number of possible quantum states, still grows exponentially.
Okay.
If you want to perfectly simulate or calculate the exact state of a highly entangled 50-qubit system, classical supercomputers start to choke. This is known as exact diagonalization.
Let me stop you there. Exact diagonalization. Let's translate that for the listener.
Imagine you have a massive, incredibly complex mathematical matrix representing all the possible states of your network. Exact diagonalization is the brute force mathematical process of finding all the foundational properties, the eigenvalues and eigenvectors of that entire matrix.
Sounds heavy.
It's like trying to understand an entire ocean by perfectly measuring the exact position and velocity of every single drop of water simultaneously. As the ocean gets bigger, doing this exactly becomes mathematically impossible. That's the exponential wall.
Got it. You can't just brute force the math, even with a quantum mindset. And what about the second threat, barren plateaus? That sounds like a geographical feature on Mars.
It's actually a topological feature of machine learning landscapes, and it's a massive problem. When you train a neural network, whether classical or quantum, it uses an optimization landscape.
Okay.
It looks for the lowest point in a valley, which represents the lowest error rate. It navigates this landscape by following gradients, which are essentially slopes pointing downwards toward the solution.
Like a ball rolling down a hill to find the bottom of a valley.
Exactly. But in deep, highly parameterized quantum circuits, a phenomenon occurs where the landscape becomes completely flat as you scale up the number of qubits. The gradients, the slopes decay exponentially fast towards zero. The landscape becomes a barren plateau.
So the ball lands on a perfectly flat plane. It has no idea which way is downhill.
Yes. In simple terms, when the machine learning algorithm tries to learn and optimize the network routing, the signals it uses to correct its mistakes vanish. The learning process literally freezes. You have built this incredibly powerful multi-million-dollar quantum machine, and it's stuck in the mud because it can't figure out which direction improves the network.
Which seems like a total deal breaker for a global 7G network. But that brings us to the savior of layer 1, tensor networks, or TNs. The literature leans heavily on these. How do they solve a completely flat mathematical landscape?
Tensor networks are fundamentally the architecture of extreme efficiency. They bypass these barren plateaus by being smart about what they actually calculate. They utilize a profound principle in quantum physics called the area law of entanglement entropy.
Okay, I promise the listener we translate the math. Area law of entanglement entropy is a mouthful. How do we visualize this?
Let's connect this to a bigger picture of how information behaves in physical space. Normally, if you want to understand a complex interacting system like a gas in a room, you have to measure the volume of the whole thing. The complexity scales with the volume.
Makes sense.
But the area law tells us something counterintuitive about the ground states of many quantum systems. It states that the entanglement entropy, which is a measure of the complex web of quantum correlations between particles, doesn't scale by the volume of the system.
It doesn't.
No. It scales only by the area or the length of the boundary of the specific subpart you are looking at.
Let me try an analogy here.
Yeah.
Let's say we want to know what's happening inside a massive, chaotic sports stadium during a championship game.
Okay.
The old way, the volume scaling way, means we feel like we need to interview every single person sitting inside the massive volume of the stadium to understand the vibe.
Right.
It takes forever, and the data is overwhelming.
Right.
But the area law says no. The truly relevant interactions can be understood just by standing at the boundaries, the exit doors, and observing the state of the people as they cross the threshold. By only looking at the perimeter, you've massively compressed the amount of information you need to process, but you still capture the essential state of the system.
That is a brilliant analogy. Yes, you ignore the overwhelming internal volume and focus on the boundary interactions. Before tensor networks, engineers were trying to interview everyone in the stadium, mathematically speaking.
Right, getting bogged down.
They were dealing with that exponential volume complexity. With tensor networks, we systematically compress that quantum complexity down into manageable polynomials. We throw away the useless data and keep only the mathematically relevant entanglement.
And the sources detail 3 core architectural shapes that these tensor networks take to encode this data. They don't just use one shape. They tailor the geometry to the problem.
Precisely. They are categorized by their dimensional structure. First, we have MPS, which stands for matrix product states.
And the schematics show MPS is basically a straight line, right? A one-dimensional chain. The text notes, it is highly effective at representing something called W states with bounded bond dimensions.
Yeah.
Again, let's translate. What is a W state?
Imagine 3 coins that are quantumly linked. A W state is a specific type of entanglement where if you flip all 3, exactly one will always land on heads and the other 2 on tails, but until you look, you don't know which one is heads.
Okay, so they are locked in a shared state.
Exactly. It represents a system where a single unit of excitation is shared equally across all the particles. MPS is incredibly efficient at mapping these linear shared state scenarios because the bounded bond dimension, the thickness of the connections in the network, remains small and manageable. It's perfect for 1D arrays of antennas.
Okay, so MPS is for straight lines. Then the second architecture is PPS, projected entangled pair states. This one looks like a grid.
Right. PPS is the workhorse for 2-dimensional and higher-dimensional quantum system research. Think of a massive grid of cellular towers covering a city. PPS strictly obeys those area laws we just discussed, making it the ideal mathematical framework for mapping a flat 2D geographic network of interactions without suffering from the exponential volume explosion.
And the third one is TTN, tree tensor networks. This is the one that really stood out to me in the research because it looks exactly like a genealogical family tree, starting with many leaves at the bottom and merging up to a single trunk.
The TTN is brilliant for hierarchical data. Its primary job is massive qubit reduction.
How does it do that?
As data flows from the leaves to the root of the tree, it systematically cuts the active qubit count by 50% between successive layers. It forces the network to distill the information, extracting only the most critical features at each junction.
So it's actively shrinking the problem.
Yes. This hierarchical compression is specifically designed to bypass those barren plateaus because you are constantly reducing the parameter space, keeping the mathematical landscape steep and navigable.
It's basically a giant tournament bracket where only the most important pieces of data advance to the next round. And by utilizing these three tensor networks, MPS, PPS, and TTN, we successfully build layer 1. We compress the impossible math.
Which is what allows us to forge layer 2, the algorithmic engine.
And this is where the literature introduces the hybrid quantum classical architecture. We don't just throw away all our classical computers, do we?
Not at all. We marry them. It's a highly specialized division of labor. The pure quantum approach is still too delicate, too noisy, but a hybrid approach leverages the best of both worlds.
How exactly does that division of labor work in this algorithmic engine? Who does what?
Think of the quantum side as the abstract savant. It handles the extremely heavy lifting of feature extraction in those high-dimensional spaces that cause classical computers to freeze.
Doing the impossible math.
Right. It uses superposition processing, multiple probabilities simultaneously, and parameterized quantum circuits to look at the massive, chaotic data stream of a 7G network and say, here are the hidden patterns, but it doesn't make the final operational decision.
It hands those patterns over to the classical side.
Exactly. The classical processing units take those quantum extracted features and use robust, well-understood algorithms like tree-based ensemble learning, random forests, and gradient boosting.
Let me jump in here. Gradient boosting and random forests. These sound like forestry terms, but they are classical machine learning techniques. They are. A random forest is basically taking 1,000 different, slightly flawed decision trees, asking them all for their opinion, and taking a majority vote to get a highly accurate answer. Right, Schmel.
That's a perfect summary. The classical side is excellent at taking abstract features, voting on them, and handling the dynamic, real-time adaptation and scalability needed to actually route the data. It provides the stability that the quantum side lacks.
The simulation results of this hybrid workflow in the sources are staggering. I mean, they ran this hybrid model against standalone classical support vector machines, which are currently top-tier classical categorization algorithms, and the hybrid approach absolutely obliterated them across every single network key performance indicator.
The numbers really speak for themselves here. In the simulated 7G environment, spectral efficiency, which is how much data you can cram into a specific radio frequency, jumped from 2.5 bits per second per hertz using classical models to 3.8 bits per second per hertz using the hybrid model.
That is a massive increase in raw data capacity without needing more actual radio spectrum.
And it did it while using less power. The energy consumption dropped from 1.2 millijoules down to 0.8 millijoules per operation.
But the metric that really matters for the future we're building is the latency, the response time.
Latency literally halved. It dropped from 10 milliseconds down to 5 milliseconds.
5 milliseconds. For context, the blink of a human eye is about 100 to 400 milliseconds. So in a fraction of a blink, this hybrid engine analyzes the network, extracts quantum features, votes on the best route, and executes. And that speed, that halving of latency, is exactly what makes Layer 3 possible.
Yes. Layer 3, the physical edge.
Here's where it gets really interesting, because everything we've talked about so far is abstract math, tensors, algorithms. Layer 3 is where this math physically interacts with the real world. We are talking about intelligent wireless power transfer, or WPT.
The 7G edge paradigm demands more than just data. It demands continuous, wire-free energy grids to support extreme connectivity. You cannot have billions of autonomous sensors and vehicles if they all have to plug into a wall every 6 hours.
Imagine you were driving an autonomous electric vehicle, an EV, down a highway. In a classical world, the network tells your car about traffic. But in a 7G world, the network isn't just sending data. It is actively managing a physical power grid to charge your car while you were driving it at 70 miles an hour, completely wirelessly.
It sounds like science fiction.
How on earth does this actually work?
The sources outline a deeply engineered resonant solution for this. It moves away from the traditional, highly inefficient methods of broadcasting power indiscriminately, and instead utilizes inductive and resonant magnetic coupling. It transfers high-efficiency power from transmitters embedded directly into the asphalt of the road, up to receivers mounted on the undercarriage of the moving vehicle.
The anatomy of this system, detailed in our sources, is incredibly specific. Let's look under the hood, pun intended. Because it's not just a big magnet. It's a highly tuned symphony of hardware.
It starts at the road level. The transmitter takes standard direct current DC power from the grid. But it can't transmit DC across an air gap efficiently. So it uses an XKT510 integrated circuit.
Which is an inverter. Right.
Exactly. This specific IC acts as a high-frequency inverter, converting the DC power into a wildly oscillating, high-frequency alternating current field, pulsing between 0 and 5 megahertz.
Millions of times a second.
Ew.
And it pushes that oscillating current through a very specific coil. The schematics detail a 24-turn copper coil with a 2-centimeter radius embedded right there in the asphalt.
That specific geometry creates a highly focused magnetic field, and the power is transmitted via mutual induction. Because the field is oscillating so fast, it reaches across the physical air gap, which the data says can be anywhere from 1 millimeter up to 200 millimeters, about 8 inches, and induces a current in the receiver coil on the car.
Okay, so the energy jumps the gap magnetically. But now the car has this wild, high-frequency, 5 megahertz AC power bouncing around its undercarriage. You can't just plug that directly into the lithium-ion battery. The battery would explode.
Right. This is where the receiver anatomy is critical. On the vehicle side, a T3168 IC receiver captures that high-frequency AC. It passes it through a sophisticated bridge rectifier setup.
And the rectifier's job is to take that oscillating sine wave and smooth it out, converting it back into stable, usable DC power.
But the car is moving, it's bouncing on suspension, the air gap is changing, the speed is changing, the power coming out of that rectifier has to be fluctuating wildly.
Which is why the smart circuitry managing this in real time is the true breakthrough. The network, powered by that 5 millisecond latency HQ-CNN we discussed, is managing this continuously. The system utilizes Arduino microcontrollers paired with infrared proximity sensors.
Right, because it's not just always on. If you blast 5 megahertz of magnetic energy into an empty road, you're wasting massive amounts of power and potentially creating hazards.
Precisely. The IR sensors and microcontrollers detect exactly when a compatible vehicle is present overhead. They trigger the specific coil directly under the car, ensuring targeted, collision-free charging. And to handle the fluctuating power you mentioned, the receiver utilizes an HW106 boost converter.
I read about this. The boost converter takes whatever variable voltage is coming in, whether the car is high off the road or low, and steps it up to a rock-solid, reliable output.
And it does it at an astonishing 93% efficiency. Almost no energy is lost as heat.
And the final gatekeeper is the TP4056 module. This component sits right before the battery. It safeguards the lithium-ion cells with strict thermal regulation and overcharge protection, ensuring the battery doesn't degrade from the constant rapid bursts of charging.
It's an incredible chain of hardware. But does it actually work in the physical world outside of a simulation?
The transition from simulation to physical prototype metrics is what makes this viable. The test systems successfully deliver a sustained 5021 watts of power safely over that 200 millimeter air gap.
5,000 watts. Wow.
Through that entire chain of hardware, the perfected sine wave reception yields a consistent 400 volt and 13 amp charge directly to the battery.
And the graphs for the state of charge, the SOC, show a flawless linear progression. There is zero recording battery degradation. For you, the listener, what this means practically is the complete elimination of range anxiety. You don't need massive heavy batteries in EVs anymore if the road itself is your battery.
And the sources note that this entire infrastructure is fully compatible with direct solar photovoltaic panel integration alongside the roadways. You are looking at zero-emission smart roads powering autonomous fleets, managed millisecond by hybrid quantum algorithms, which are in turn mathematically stabilized by tensor networks.
That complete chain is the converged 7G ecosystem.
It is breathtaking.
But as much as I want to jump straight into that future, the reality is we can't just flip a switch from 5G to quantum 7G. We have to build a bridge. We have to navigate the transition period. And that bridge, which forms part 2 of our deep dive, is 6G, the AI-native and quantum-ready communication revolution.
6G is the necessary scaffolding. You can't deploy quantum spectrum management without first deploying a network architecture capable of housing it.
Let's talk about the sheer performance capabilities of 6G, because even without the full quantum backend, the numbers are astronomical. 6G aims to achieve 1 terabit per second TBPS data transfer rates. We're talking about leaping from the gigabit scale we are just getting used to straight into the terabit scale.
To put 1 terabit per second into perspective, people often say it allows you to download hundreds of 4K movies in a single second.
Right.
But that's a very superficial way to look at it.
Right, because nobody actually needs to download 500 movies a second. What is the real implication of a terabit per second?
The implication is that at 1 terabit per second, Combined with microsecond latency, the very concept of buffering, loading, or even local storage ceases to exist. We transition from a world where we actively retrieve data to a world where data is simply present around us at all times, like oxygen.
Your devices don't need hard drives. They just pull whatever application or environment they need instantly from the network edge.
Exactly. And it enables what the industry calls URLLC, ultra-reliable low-latency communications. When the network response times drop to the microsecond level, they are practically instantaneous.
And that instantaneous reliability is what supports massive hyperconnectivity. 6G is designed to support massive IoT, connecting tens of billions of devices simultaneously with incredibly high energy efficiency. So how does 6G actually achieve this bridge? Our sources lay out 4 core technological pillars.
Let's walk through those pillars, because this is how they are laying the tracks right now. Pillar 1 is an AI native architecture, and the key word there is native.
Because right now AI is just an add-on.
Exactly. In our current 4G and 5G networks, artificial intelligence is layered on top. It's an afterthought, a software patch trying to optimize a rigid hardware system. In 6G, AI is integrated directly into the physical and logical foundation from day one.
It doesn't just monitor the network. It is the network. It handles dynamic resource allocation, predictive analysis, and real-time self-optimization without human intervention.
Pillar 2 is expanded spectrum usage. We are running out of invisible real estate in the air. 6G will heavily utilize centimetric waves, that's the 7 to 15 gigahertz range, to provide incredibly dense urban coverage. But for those mind-bending terabit peak data rates, it taps into the sub-terahertz bands, pushing up above 100 gigahertz.
And Pillar 3 addresses the physical topology. Seamless network integration. Currently, our networks are largely two-dimensional. They rely on cell towers planted on the ground. 6G breaks the z-axis.
It merges terrestrial ground networks with non-terrestrial components, thousands of satellites in low Earth orbit, high-altitude platform stations, and aerial drones to create a ubiquitous, truly 3D planetary coverage blanket.
You could be in the middle of the Sahara Desert and have the exact same terabit connection as someone in downtown Manhattan.
Exactly. And Pillar 4 encompasses advanced architectures. This includes the deployment of things like reconfigurable intelligent surfaces, or RIS. I love this concept.
RIS is fascinating. They're essentially programmable smart mirrors for radio waves.
Right.
Instead of a signal hitting a building and dying, an RIS panel on the side of the building detects the signal, mathematically reconfigures its surface using metamaterials, and perfectly bounces and directs the radio wave exactly to your device around corners and obstacles.
6G also relies on Open RAN, open radio access networks to prevent hardware monopolies, and edge computing to process data close to the user.
This sounds utopian. But if I'm playing devil's advocate, this raises a massive, terrifying question. With this level of hyperconnectivity, where your car, your heart monitor, and your bank are all instantly connected on an AI-managed network, the security vulnerabilities become monumental. A single breach could paralyze a city.
That is the most critical vulnerability of the 6G bridge, and it brings us to the quantum shift and security protocols outlined in the research. The sources are very clear. 6G must defend against sophisticated AI-driven attacks, but far more pressingly, it faces the existential threat of Q-Day, the day a quantum computer becomes powerful enough to break classical RSA encryption.
Right. RSA encryption is the bedrock of almost all internet security today. Every time you log into your bank, buy something online, or send a secure message, RSA is protecting you. It relies on a mathematical trick. It's incredibly easy for a computer to multiply two massive prime numbers together, but it takes classical supercomputers thousands of years to do the reverse, to take the massive resulting number and figure out which two prime numbers created it.
That's the classical assumption. But quantum computers, specifically running algorithms like Shor's algorithm, don't need to guess one by one. Using superposition, they can factor massive prime numbers in hours or even minutes.
Once that happens, the encryption of the world shatters. Financial data, government secrets, personal communications, all exposed simultaneously.
So how does 6G defend against a machine that can break math itself? By moving away from mathematical complexity and relying on the fundamental laws of physics, 6G must implement next-gen defense mechanisms, specifically quantum key distribution, or QKD.
How does QKD physically work? Why is it unhackable?
QKD uses single photons, particles of light in specific quantum states to generate a secure cryptographic key between two parties. The security relies on a core principle of quantum mechanics. The act of measuring a quantum system irreversibly alters its state.
Oh, this is the observer effect.
Exactly. If a hacker tries to intercept the photons mid-transmission to read the key, their very act of looking causes the quantum state of the photon to collapse. The photons arrive at the destination altered.
And the system notices that immediately.
Yes. The system instantly detects this anomaly, knows the channel is compromised, discards the key, and tries a new path. It is physically impossible to intercept the key without leaving an undeniable trace.
It's like sending a letter in an envelope that instantly bursts into flames if anyone other than the intended recipient even looks at it. And the sources show they are pairing this QKD with advanced decentralized blockchain technology to ensure that the ledger of network integrity cannot be tampered with by any single bad actor.
So when you synthesize all of this, the terabit speeds, the AI native optimization, the physics-based quantum security, you begin to see the practical realities for the user. The future application scenarios outlined in our materials are transformative.
Let's ground this for the listener. We talked about autonomous mobility earlier, but it's that microsecond latency we discussed that actually allows a swarm of vehicles moving at high speeds to make real-time decisions, coordinating not just with each other, but with the RAS panels and the smart road infrastructure safely. But the application that really shocked me was digital healthcare.
Telesurgery is the prime example.
Yes, we're talking about a specialist surgeon in New York operating a robotic surgical arm on a patient in a rural clinic in Tokyo. With classical networks, even a 50-millisecond lag means the surgeon could accidentally sever an artery. But with 6G URLLC, the surgeon feels the tactile feedback of the scalpel in real time without a millisecond of lag.
Add to that the integration of AI-driven real-time patient monitoring systems, where continuous biometric data is fed to the cloud and analyzed instantly to predict a cardiac event minutes before it happens.
And finally, immersive experiences. 6G is the underlying requirement for true extended reality and holographic telepresence. We won't be staring at flat screens on video calls. We will be interacting in lifelike 3D remote environments projected directly into our retinas or living rooms.
But here's the crux of the transition. To run all of these 6G applications and to eventually scale them into the 7G ecosystem, the underlying brain of the network has to evolve. You cannot run these quantum-secure terabit networks with classical AI.
This brings us to part 3 of our deep dive. Deep quantum neural networks, the actual engines driving this evolution.
Let's recalibrate and reiterate the 6G, 7G imperative. The requirements are immense. We need those terabit speeds, the microsecond latency, and we need to manage what the literature calls UDNs, ultra-dense networks.
And as we mentioned, these networks aren't flat anymore. They are volumetrically layered across terrestrial base stations, aerial drones, and non-terrestrial satellites.
To manage a multi-layered 3D ultra-dense network, the fundamental unit of classical computation, the classical bit simply fails. It lacks the dimensionality. The deep quantum neural network engine must rely entirely on the qubit.
This is a concept we hear thrown around a lot in pop science, but let's define it clearly for the listener. What is the functional difference between a bit and a qubit in the context of routing a global network?
A classical bit is a mechanical switch. It is entirely binary and rigid. It is either off or on, a 0 or a 1. A qubit, conversely, is typically visualized mathematically as a point on the surface of a sphere known as a Bloch sphere. It leverages superposition.
Right, so it's not just a simple switch.
No. Superposition allows the qubit to process simultaneous states. It isn't just a 0 or a 1. It represents a weighted probability of being both 0 and 1 at the exact same time until it is measured.
How does that apply to the network?
Imagine an orchestra. A classical bit is a single violin playing one note. A qubit is the entire orchestra playing a complex chord simultaneously. It allows the neural network to evaluate thousands of potential routing paths across the satellite and ground network all at once, rather than checking them sequentially.
And then it pairs that superposition with entanglement, which you mentioned earlier. Entanglement provides instant correlation across nodes. If a qubit on a satellite in orbit is entangled with a qubit in a base station on the ground, changing the state of one instantly affects the other,
completely bypassing the physical distance and the speed of light delay that traditional radio waves suffer from.
When you build neural networks using these qubits, you create QNNs, quantum neural networks. And when we look at the source data to see where our layer 1 tensor networks are currently being applied within these QNNs, the distribution is very telling about where the industry is heading. It's no longer just theoretical physics experiments.
The application chart is fascinating. 30% of tensor network application is going directly into quantum simulation modeling new materials. 25% is dedicated to image classification, which is vital for autonomous vision.
20% to quantum chemistry for drug discovery. 15% is focused on data compression, which we will see is crucial for bandwidth. And 10% is allocated to multimodal fusion.
That diverse application distribution is exactly what supports the overarching architecture, the HQCNN, or Hybrid Quantum Classical Convolutional Neural Network. Again, as we saw in Layer 2, classical layers ensure structural stability, while the quantum layers provide the massive abstraction power.
Our research stack identifies the 4 pillars of the HQCNN that make this entire 6G, 7G cognitive infrastructure possible. Let's break down these 4 pillars.
Pillar 1 is intelligent spectrum management. This involves the real-time classification of the chaotic terahertz frequency bands to allow for dynamic frequency reuse. We are going to dedicate the entire final part of this deep dive to exactly how this works, but the short version is, it's the system that ensures the massive amounts of invisible data flying through the air don't crash into each other.
Correct. Pillar 2 is edge intelligence and federated learning. Federated learning is a great concept. Instead of sending all your private data to a central cloud to be analyzed, which is slow and insecure, the learning happens locally.
Exactly. This pushes the optimization directly to the network edge, right where the user is, which is how you achieve that ultra-low latency. An IoT device, say a smart traffic light, collects raw data. It sends it to a localized quantum edge node.
And what does the node do?
That node uses quantum feature extraction to make a real-time decision, like changing the light to prevent an accident, while securely sending only the mathematical updates, not the raw video data, back to the cloud layer to improve the global model.
And the field experiments highlighted in the data for this are staggering. They show a 78% faster convergence in beam prediction using this federated quantum method compared to classical centralized cloud processing. It learns 78% faster.
Pillar 3 is one that I believe will define the public acceptance of this technology, the green network. It focuses aggressively on energy efficiency.
This is a crucial point because running massive AI models like large language models or global routing networks consumes horrific amounts of power. Server farms are draining local power grids right now.
They are, but the quantum-optimized architectures detailed in our sources intrinsically minimize MXC operations.
The MXC operation.
Multiply-accumulate operations. It's the core mathematical function of classical neural networks. A classical AI does billions of these a second, burning energy. The hybrid quantum approach reduces the need for these brute force MPass operations by an incredible 40 to 60%.
And it does it while being faster. The source provides a concrete example. The computation time for high-resolution vehicle detection in a smart city grid drops from 3.2 seconds classically down to 1.5 seconds using the hybrid quantum classical approach.
You are cutting the compute time in half and cutting the energy consumption in half. That is the only way an ultra-dense network becomes ecologically sustainable.
And finally, Pillar 4 is quantum-grade security embedded directly into the AI pipeline. We touched on QKD for transmission, but the QNN pipeline itself is mathematically secure by design.
Walk us through that secure pipeline. How does data move through it without being exposed?
Data is collected from mobile sensors. Before it even moves, it is pre-processed and massively compressed via tensor decomposition. This compressed data is then sent through 2 simultaneous pipelines, a classical tensor neural network and a quantum encoding layer that feeds into a QNN.
And because the data in the quantum pipeline exists in superposition, it cannot be read by an intruder without collapsing. Those 2 outputs merge seamlessly at a fusion layer, which makes the final decision before initiating a physical control action. It's an incredibly robust, multi-layered security architecture.
To see this engine actually working, let's look at the deep dive applications the sources highlight.
Yes.
Let's go back to V2X, vehicle-to-everything autonomous mobility. Powered by this HQCNN, the testing achieves an 82 millisecond emergency braking latency across the entire network.
Which is vastly faster than human reaction time.
Exactly. It hits a 94% collision avoidance accuracy in dense simulations, and crucially, it manages a 98% compression rate on LiDAR point clouds.
That compression statistic is vital. LiDAR, which uses lasers to map a 3D environment, generates immense, unwieldy amounts of data. A single autonomous car produces terabytes of LiDAR data an hour. You cannot transmit that raw data over a network.
No network can handle it.
The quantum engine's ability to compress that by 98% without losing the geometric fidelity of the environment is what makes connected autonomous driving possible.
Another application is the smart home ecosystem. Right now, a hacker can theoretically access your home network through a vulnerable smart light bulb. But in this architecture, all your connected devices and sensors are routed through a localized quantum edge gateway.
It utilizes that quantum security pipeline to talk to the cloud server, making IoT hijacking practically impossible by the laws of physics.
And then there is the healthcare digital twin application. This truly pushes the boundary of what we consider reality.
Imagine wearing an advanced VR headset connected via a 6G low-latency link. The tech stack shows holographic communication interacting directly with the user.
While you're interacting with a doctor's avatar, a QNN is actively running complex emotional and biometric analysis based on your microexpressions and vital signs. All of this is secured by a blockchain layer handling decentralized trust, ensuring your medical data is untouchable.
You essentially have a fully synchronized digital twin of your own biology being monitored and analyzed in real time by a quantum neural network to predict and prevent health events before they physically manifest.
It is absolutely revolutionary. However, as analysts, we must remain grounded in the current physical reality of the hardware required to run this. And that reality is fraught with challenges. We are currently navigating what the industry refers to as the NISQ era.
NISQ, noisy intermediate scale quantum hardware.
Correct. We don't have perfect quantum computers yet. We have intermediate scale ones, and they are notoriously noisy.
When we say noisy, we don't mean they're loud. We mean they're incredibly sensitive to environmental interference.
Exactly. The qubits are delicate quantum states. Minute fluctuations in heat, ambient electromagnetic interference from emitted by a cell phone, or even cosmic rays striking the processor from space can cause decoherence.
The quantum state collapses prematurely, introducing errors or noise into the calculation.
Which begs the question, if the hardware is so fragile that a cosmic ray can disrupt it, how can we possibly trust it to manage city traffic or a digital medical twin?
That is the exact problem researchers are tackling.
Yeah.
Bridging this gap of restricted qubit connectivity and incredibly short coherence times requires a tight feedback loop between the experimental physicists building the hardware and the theorists writing the algorithms. But there is incredibly good news buried in the research data regarding this noise.
Let's hear the good news, because the cosmic rays have me worried.
The data proves that these specific hybrid HQCNN models are mathematically robust enough to maintain high accuracy even when running on this noisy NISQ hardware. The classical parts of the hybrid network act as an anchor. The sources show a test where they evaluated the QNN's accuracy on standard image recognition datasets, specifically the MNEST and Fashion MNEST databases, both before and after artificially introducing severe quantum noise.
And what was the drop in performance? Did the network fail?
The drop was negligible. On the standard MNEST data, accuracy only dropped from 98.7% down to 98.6%.
That's nothing.
On the more complex Fashion MNEST data, it went from 88.3% to 87.2%. The hybrid architecture absorbs the quantum errors and corrects them. It was remarkably resilient.
Okay, that resilience is the perfect setup for part 4. This is the climax of our deep dive. We have built a mathematical foundation with tensors, we've crossed the 6G terabit bridge, and we've looked deeply under the hood of the hybrid quantum neural network engine. Now we have to tackle the hardest, most vital logistical puzzle on Earth.
Managing the actual physical invisible radio waves that make all of this possible. This is quantum spectrum management.
Everything we have discussed relies on transmitting data through the air. And the transition from classical deep learning to quantum parallelism is most urgently needed right here because we are facing the 6G, 7G spectrum crunch.
Put simply, we are running out of usable airwaves. The invisible real estate above our heads is full.
Completely gridlocked. To understand why quantum is needed, we need to map out the current traffic jam. Let's look at the 4 main radio frequency bands being utilized. Let's start from the bottom and work our way up.
First, you have the sub-6 gigahertz band, specifically the 3.2 to 3.5 gigahertz range. If you look at your 5G phone right now, this is likely what it's using.
The signal penetrates buildings well, it travels far. The problem? Total congestion. It is utterly crowded with massive IoT density. It's a 6-lane highway with 10,000 cars trying to merge at once.
Moving up the frequency spectrum, we enter the centimetric waves, spanning the 7 to 15 gigahertz range. The friction here is the eternal physics balancing act of coverage versus capacity. Because the frequency is higher, the waves are shorter.
They can carry significantly more data, higher capacity, but the signal doesn't travel as far, and it struggles to penetrate concrete and steel.
Then we step into millimeter wave, operating between 28 and 40 gigahertz. This is where you start getting those incredible gigabit speeds. But the physical friction here is severe atmospheric absorption.
Yes, this is where the environment itself becomes the enemy. At these tiny wavelengths, physical raindrops, high humidity, and even oxygen molecules in the air act as physical barriers that absorb and scatter the signal. You can have a perfect wave connection, and a heavy rainstorm will drop your call.
And finally, we reach the frontier. The sub-terahertz bands, operating at 100 plus gigahertz. This is the holy grail. This is where you unlock those terabit speeds we talked about for 6G.
But the friction is extreme path loss. The signal degrades incredibly fast over even short distances. If you turn your back to the transmitter, your own body might block the signal.
The key takeaway from the operational data is that classical deep learning algorithms simply cannot handle high-resolution spectrum sensing across all these wildly different physical constraints at the microsecond speeds required.
You cannot use a classical computer to dynamically switch a million devices between sub-6 gigahertz and sub-terahertz bands while accounting for rain, buildings, and movement. The computational load is too high.
And this is exactly where the math we explored in part 1 comes back in a huge practical way. The logarithmic advantage. Let's compare the computational complexities of managing this spectrum.
If you use a classical convolutional neural network, a CNN, to manage this high-dimensional spectrum data, the algorithm requires massive arrays of hardware. Its computational complexity scales at O(n) squared. As the spectrum channels double, the required processing power quadruples.
But if we deploy a quantum convolutional neural network, a QCNN, we fundamentally change the math. The QCNN operates with a complexity of O log n.
By shifting the methodology from classical linear convolution to quantum entanglement, we utilize exponentially fewer parameters to reach the exact same analytical conclusion.
This O log n scaling is the magic key. It is what allows us to process these massive terahertz band signals in real time on the near-term NISQ devices we just discussed.
The sources outline exactly how this data compression works, and this was the biggest aha moment for me in the entire stack. They demonstrate compressing the spectrum data using a technique called amplitude encoding.
Amplitude encoding is brilliant. It maps the classical data into the probability amplitudes of a quantum state.
Let's visualize this. The data shows they take a 64-channel power spectral density input. Imagine a massive 64-lane superhighway of invisible radio traffic with data constantly shifting lanes. In a classical system, you need 64 separate processing nodes to monitor each lane. But with amplitude encoding, they encode the entire state of all 64 lanes simultaneously in superposition into a system containing just 6 qubits.
Exactly, because 2 to the power of 6 is 64. Those 6 qubits, entangled together, hold the entirety of the 64-channel matrix.
But wait, if I'm the listener, I'm highly skeptical right now. You're telling me you are cramming 64 lanes of dense data into 6 tiny qubits. How are we not just throwing massive amounts of data off a bridge? How does the network not just drop the call?
Because of the nature of quantum amplitudes, you aren't deleting the data, you are translating its structure into a geometric state. The relations between the data points, the peaks of interference, the valleys of open bandwidth are perfectly preserved within the entangled web of those 6 qubits.
That translation yields a 10.7x compression ratio compared to classical methods without losing the critical relational data needed to route traffic.
That is a staggering increase in efficiency. Let's take the listener inside the quantum circuit itself to see how a QCNN processes those 6 qubits, because it's not like a standard silicon chip.
It's completely different. The end-to-end workflow begins with that data encoding we just discussed. Once the data is a quantum state, the circuit uses parameterized quantum circuits, or PQCs. These PQCs utilize specific entangling gates, primarily CZ and CNT gates, to detect spectral features in what we call a convolutional layer.
Let's pause and explain these gates, CZ and CNOT. In classical computing, we have AND, OR, and NOT gates. How do quantum gates work?
Think of a CNOT gate, a controlled NOT gate, like a highly complex interdependent set of train track switches. You have a control train, qubit A, and a target train, qubit B. If the control train is painted blue, representing a state of 0, the target train passes through the switch untouched.
But if the control train is painted red, state 1, the switch physically flips the track, causing the target train to invert its state.
But remember, because of superposition, the control train can be both red and blue at the same time, meaning the target train is both flipped and untouched simultaneously. These gates entangle the qubits, weaving their fates together to reveal patterns in the data.
So the convolutional layer uses these intricate switches to look for patterns like a massive spike in interference on lane 12. What happens next?
Following the convolution, the quantum circuit employs a pooling layer. The goal here is dimensionality reduction. It literally measures a subset of the qubits. By measuring them, it collapses their state, effectively tossing out the unneeded, redundant background data while retaining the highly compressed, critical features in the remaining unmeasured qubits.
It's constantly distilling the data. It repeats this convolution and pooling process, entangling, pattern finding, measuring, discarding, until it outputs the final optimized routing signal.
And because of quantum feature mapping, this entire process happens at speeds classical physics can't touch. Parallel processing means a single quantum filter evaluates every single frequency configuration simultaneously.
So for that 64-channel spectrum that we encoded into 6 qubits, the system doesn't check lane 1, then lane 2, then lane 3. It evaluates 2 to the power of 6, all 64 configurations in a single instantaneous mathematical pass.
The resulting output is sub-millisecond feature extraction. The network knows exactly where the open spectrum is instantly. That speed is the absolute prerequisite to enable real-time LM wave massive MIMO beamforming.
Massive MIMO beamforming. That's essentially the antenna detecting exactly where your phone is in 3D space. And rather than broadcasting a signal everywhere in a circle, it directs a highly focused, laser-like beam of data directly to your device faster than a blink of an eye.
Exactly. To prove this architecture works, the scientific editorial in our sources presents a deeply detailed case study on dynamic frequency reuse.
Let's set the scene for this case study. Imagine a highly dense urban 6G base station, say in Times Square. It is packed with 200 active devices per square kilometer. Autonomous cars, VR headsets, smartphones, all demanding high bandwidth simultaneously.
The spectrum grid is highly volatile. It's divided into hexagonal physical zones that are experiencing wildly different states. Some have severe interference, some are moderately congested, and some are temporarily free for reuse.
The researchers ran a simulation contest between 3 different models to see which could best manage this chaotic shift of spectrum. A 6-qubit QCNN, a state-of-the-art classical CNN, and a standard classical logistic regression model.
The performance gap is undeniable. The QCNN absolutely dominates. It identifies the reusable spectrum blocks with much higher precision. The QCNN achieved a mapping accuracy of 92.3% compared to the classical CNN's 85.1%.
But the latency and the energy numbers are where the classical models truly look obsolete. The QCNN was 3.8 times faster, clocking a processing latency of just 1.2 milliseconds versus the classical CNN's 4.6 milliseconds.
And it did this while consuming less than half the energy. 5.2 millijoules compared to 12.4 millijoules.
It's faster, more accurate, and greener. However, our sources are rigorously scientific. They do not hide the flaws. There is a catch in the precision versus confusion data that we need to talk about.
Yes, there is an algorithmic weakness. While the QCNN had an astounding 94.2% precision success rate in detecting areas of high, distinct interference via entanglement patterns, it actually struggled in moderately congested, messy scenarios. In those edge cases, it produced 12% false positive, where it thought a channel was full when it was actually available.
The root cause analysis in the data points to something very specific. It says that overlapping NOMA signals, specifically QPSK and QAM modulations, can fundamentally confuse the quantum feature map.
Okay, let's unpack those modulations. QPSK and QAM sound like radio station call signs.
They are ways of packing data onto a radio wave. QPSK stands for quadrature phase shift keying, and QAM is quadrature amplitude modulation. Think of a radio wave as a continuous squiggle. You can change its height or amplitude or shift its starting point phase to represent a 1 or a 0.
QPSK and QAM are incredibly dense ways of doing this, packing multiple bits of data into a single squiggle.
And NOMA.
Non-orthogonal, multiple access. It means you're allowing multiple users to transmit their squiggles on the exact same frequency at the exact same time, just at different power levels.
Oh, wow. So you have multiple users all using highly dense, overlapping wave manipulations on the same frequency. It's an absolute cacophony of data.
Precisely. And in moderately congested areas, the quantum feature map struggles to disentangle the overlapping QPSK and QAM signals. The mathematical shapes blur together in the superposition state, leading to that 12% confusion rate. This highlights a clear, immediate need for further algorithmic refinement in the pooling layers to better separate these complex modulations.
And that algorithmic flaw brings us to the final reality check: the physical barriers. The NISQ barrier we discussed earlier rears its head again when we talk about actual hardware deployment.
We mentioned quantum noise from cosmic rays, but in the context of spectrum management, you have a massive local problem: electromagnetic interference, or EMI. A base station is a highly charged electromagnetic environment. That EMI causes rapid decoherence of the quantum signal path. The research attributes a full 22% accuracy drop in unprotected testing environments directly to EMI noise.
Furthermore, those barren plateaus we discussed in Part 1, where the learning gradients vanish during training, continue to hinder the rapid convergence of these models in the field.
But the physical bottleneck that is perhaps the most daunting is the RF to qubit latency.
This one blew my mind when I realized the physical constraints. The system has to capture analog radio frequencies from the air and physically convert them into quantum states to be processed by the QPU. Doing that currently requires specialized hardware called cryogenic analog-to-digital converters, or ADCs.
Exactly. Quantum processors must operate at cryogenic temperatures near absolute zero to maintain superposition. But radio waves are hot, energetic analog signals. The hardware required to bridge that thermal and physical gap adds a processing delay of 5 to 15 milliseconds.
Which completely destroys the 1.2 millisecond processing time of the algorithm. It directly threatens the microsecond URLLC targets we desperately need for 6G. If the converter takes 15 milliseconds, the autonomous car has already crashed.
So how do engineers build workarounds for the laws of thermodynamics? The sources detail three main approaches currently in development. First is software error mitigation.
By using advanced mathematical techniques like zero-noise extrapolation, or ZNE, and polytrolled embedding layers, the engineers can mathematically reconstruct the degraded signal. The data shows this software approach recovers 12 to 18% of that lost accuracy without needing to change the hardware.
The second approach is hybrid offloading. If the cryogenic quantum hardware is physically bottlenecked by latency, the system architecture adapts. They take the heaviest, most mathematically complex convolution tasks and offload them to advanced quantum simulators.
The sources specifically mention simulators like PennyLane's Lightning GPU, so they use massively parallel classical GPUs to perfectly simulate a quantum environment, bypassing the cryogenic bottleneck entirely while keeping the pooling and decision layers strictly classical.
And the third and ultimate approach is hardware innovation. The industry is currently aggressively prototyping direct RF to qubit conversion technologies. These utilize specialized electro-optic or optomechanical transducers designed specifically to bypass that cryogenic ADC latency bottleneck entirely, injecting the radio signal directly into the quantum state.
So let's step back and look at the big picture. We've gone through the quantum physics, the deep neural networks, the terabit antennas, the cryogenic constraints. What does this all mean? When they pour the concrete and run the fiber, how does this actually get built into the world? The schematics in our sources give us the final hybrid topology.
It is visualized as a deeply integrated three-tiered hierarchical system. Let's start at the edge where the user is. Tier 1 is the mobile frontal.
This is your user equipment, your 6G smartphones, the sensors in your autonomous EV, the VR headset. These connect wirelessly to edge antennas known as remote radio heads, which are physically connected via massive optical fiber cables.
That optical fiber frontal links directly back to Tier 2, the centralized data center. This is where baseband processing occurs, and this is where the true architectural revolution happens. Inside these centers, you will have advanced classical processing units sitting side by side, physically wired to quantum processing units, or QPUs.
They operate in tandem. The QPU specifically handles the massively parallel tasks: the fast Fourier transforms that break down the radio waves, the hypercomplex channel estimation we talked about with the 64 lanes, and the quantum error control. It extracts the insights and instantly hands them to the classical unit to execute the routing.
And finally, Tier 3 consists of high-capacity backhaul links that connect those centralized data centers into the global mobile core network, the IP core, and the next-generation core, tying the entire planet together.
This detailed topology gives us our definitive roadmap to 7G. It happens in two distinct phases. Phase 1, which is dictated by the current maturity of NISQ hardware, is hybrid 6G. This is the bridge. In Phase 1, QCNNs are used selectively for very specific mathematically impossible tasks, like minimum wave beamforming and dynamic spectrum sensing, but they always have a robust classical network fallback in case the quantum hardware decoheres or fails.
But Phase 2 is the ultimate destination, native quantum 7G. This is the goal.
In Phase 2, the classical fallback is removed. We transition to end-to-end QCNNs, enabling flawless, real-time optimization of the volatile 100-plus gigahertz sub-terahertz bands. This is what makes true lag-free holographic communications, massive autonomous swarms, and a seamlessly integrated physical-digital metaverse a living reality.
The overarching quantum paradigm shift, detailed in every single paper we've reviewed, proves one unavoidable fact. Transitioning from the O(n) squared complexity of classical computing to the O log n parameters of massive quantum parallelism is not just an upgrade, it is the mandatory evolutionary step required to unlock intelligent spectrum management and sustain human technological growth.
We have covered an immense, almost overwhelming amount of ground today.
We started by looking at the crumbling foundations of our current classical networks, paralyzed by the factorial curse of dimensionality. We explored the elegant, mind-bending mathematical compression of tensor networks and the boundary rules of entanglement entropy.
We crossed the 6G bridge of terabit speeds, physics-based unhackable security, and AI-native architecture.
We looked deep under the hood of the deep quantum neural network engine, analyzing bit versus qubit and the incredible energy savings of hybrid processing.
And finally, we navigated the incredibly complex, volatile physics of quantum spectrum management, from amplitude encoding 64 lanes of traffic into 6 qubits to the cryogenic realities of hardware bottlenecks.
It is a profound transition. By mathematically marrying quantum mechanics with classical machine learning, engineers are not just finding ways to speed up existing algorithms. They're entirely reimagining the physical limits of data processing, redefining secure communications, and designing a sustainable, intelligent physical infrastructure capable of supporting human society for the next century.
Exactly. I want you, the listener, the next time your Wi-Fi drops or your GPS glitches, to remember the massive, invisible architecture being built to solve it.
This isn't just theory. We are looking at a near, tangible future. A future with seamless autonomous vehicles powered indefinitely by oscillating magnetic fields embedded in the very roads they drive on. We are talking about the reality of remote, perfectly synchronized holographic medical care that could save lives across the globe, regardless of geography. And we are talking about an absolute end to dropped calls, latency, and congested networks, even in the most densely packed, hyperconnected cities on Earth.
It's an inspiring vision of engineering, but I will leave you, the listener, with a final, perhaps more philosophical thought based on everything we have unpacked today. We are building a nervous system for the planet based on quantum rules.
If our entire global communication infrastructure ultimately operates on the principles of quantum superposition and entanglement, where fundamental data exists in multiple probability states at once and instantaneously correlates across vast physical distances without regard for the speed of light, how long until that ubiquitous technology fundamentally changes not just how our machines talk to each other, but how we humans perceive time, distance, and reality itself?
A profound and slightly dizzying question to end on.
Thank you so much for joining us on this deep dive into the 6G and 7G quantum frontier. We will see you next time.